Hello everyone, welcome to my channel Learn Physics with MPG. I am Dr. Mrityunjay Prasad Ghosh, currently working as an assistant professor at SR University, Warangal, Telangana, India. So today we are going to discuss some important topics related to electrostatics. So we will discuss basic concept of electrostatics. Further, we will go through Coulomb's law, Gauss law of electrostatics, and then we will solve some numerical problems based on Coulomb's law, right? So let's start the discussion. So first we will discuss what is electric charge or electrical charge, right? So electric charge is an entity that can be either positive or negative and which is carried by fundamental particles like electron and proton. So what are the fundamental particles? So electron and proton are fundamental particles because they are not made of quark or anti-quark, right? So electron and proton are the fundamental particles. So what is charge? That can be either positive or negative, right? Charge can be either positive or negative. So what is a electrical charge or electric charge? So which is an entity that is carried by fundamental particles like electron and protons, and it can be either positive or negative, right? So this is the definition of electric charge or electrical charge. So now we will discuss few unique properties or characteristic of electrical charge or electric charge, right? So charge is a scalar quantity, right? So charge has only magnitude, no direction. So charge is a scalar quantity and it is measured in coulombs. So what is the unit of charge? The unit of charge is coulomb, right? What is the one electronic charge? One electronic charge is equal to 1.6 into 10 to the power minus 19 coulomb, right? 10 to the power minus 19 10 to the power minus 19 coulomb, right? So this is the value of one electronic charge. So charge is a scalar quantity, so it has only magnitude, no direction, and it is measured in terms of coulomb, right? The smallest possible charge that correspond to a one electron. What is the smallest possible charge? That is one electronic charge, which is equal to 1.6 into 10 to the power minus 19 coulomb, right? For electron, the magnitude of electronic charge is 1.6 and it is negative, right? Magnitude is 1.6 into 10 to the power 19, 10 to the power minus 19 coulomb, but it is negative. For proton, the magnitude is same, that is 1.6 into 10 to the power minus 19 coulomb, but the charge is positive in nature, right? One electronic charge is positive for proton and for electron it is negative, and the magnitude is 1.6 into 10 to the power minus 19 coulomb, right? This is the smallest possible electronic charge which is correspond to one electron, right? And this smallest possible value of charge can transfer, right, which is equal to 1.6 into 10 to the power minus 19 coulomb. What is the another unique property of electric charge? That is charge is conserved, which means charge is neither created nor destroyed. So charge cannot be created or can't be destroyed, right? So charge is conserved. What is the next unique property of electrical charge? That is charge is quantized, right? So what does it mean? So electrical charge is not continuous. It can exist in individual or discrete packets, right? So electrical charge is quantized. So it is not continuous. So it can exist in discrete and individual packets, right? So these are the unique properties of electrical charge. So electrical charge can be either positive or negative, right? It is a scalar quantity. It is measured by coulomb, right? So the unit of charge is coulomb. The smallest possible charge that correspond to an electron is 1.6 into 10 to the minus 19 coulomb, right? So charge is conserved, which cannot be created or not destroyed. so which is neither created nor destroyed, and charge is quantized in nature, so it is not continuous, so it can exist only in individual or discrete packets, right? So these are the unique properties of charge. So let's move to the next slide. Some classic examples of electrostatic attraction. So in the first example, if you take a glass rod and a piece of silk cloth, and when the glass rod is wrapped with silk cloth, then the electron from the glass rod are transferred to the silk because silk has high electron affinity. As a result, the glass rod becomes positively charged and silk cloth becomes negatively charged. So they can attract each other through electrostatic attraction. Right? In the second example, if you take a comb and after rubbing a comb through hair on a dry day, the comb will attract some piece of papers, right? So if you take a comb and if you rub it through hair on a dry day, or if you rub a comb through dry hair, then the comb will start to attract some piece of papers, right? So this is a classic example of electrostatic attraction. Hope you get it. So let's move to the next slide. So now we will discuss Coulomb's law. So we will go through the statement of Coulomb's law, right? So if two point charges are separated by a linear distance, so this is a point charge Q1 and this is another point charge Q2. So if two point charges Q1 and Q2 are separated by a linear distance r, right? So they can exert force to each other, or they can exert force on each other along the joining line, right? The force can be either attractive or repulsive depending upon the nature of charges, right? So when two point charges Q1 and Q2 are separated by a linear distance r, then they can exert attractive or repulsive force on each other along the joining line, right? So this is the joining line, and the magnitude of this electrostatic force, which can be either attractive or repulsive depending upon the nature of the electrical charges. So the magnitude of the electrostatic force is proportional to the magnitude of charges, right? So F, that is the magnitude of the electrostatic force, is proportional to the magnitude of charges, that is F proportional to Q1 into Q2, right? And this force, the magnitude of this electrostatic force is inversely proportional to the square of the distance between them. So here capital R is the distance or the linear distance between these 2 point charges Q1 and Q2. So the magnitude of the force F is inversely proportional to the square of the distance between these 2 point changes, right? So F varies 1 by R square, right? So together we can write F is proportional to Q1 Q2 by R square. So we need a proportionality constant. So F equal to K Q1 Q2 by R square, right? So F is proportional to Q1 Q2 by R square, where Q1 Q2 is the magnitude of point charges and R is the distance between them. So F is proportional to Q1 Q2 by R square, or F equal to K Q1 Q2 by R square, where K is called the proportionality constant, which is equal to 1 by 4 pi epsilon. Epsilon is dielectric permittivity, right, or permittivity. So epsilon is permittivity of a medium, right? So epsilon is called the permittivity of a medium in which the point charges are placed, right? So where k is the proportionality constant, which is equal to 1 by 4 pi epsilon, where epsilon is permittivity of the medium in which the point charge q1, q2 are placed, right? So in vacuum or in free space, k is equal to 1 by 4 pi epsilon naught, where epsilon naught is the permittivity in free space or vacuum, right? Did you get it? So now move to the next slide. So epsilon is the permittivity of a particular medium in which the two point charges q1, q2 are placed, right? Where epsilon naught is the permittivity in free space or vacuum, right? So epsilon r is called the relative permittivity, right? Epsilon r. So epsilon r equal to epsilon by epsilon naught. So epsilon is the relativity of a medium divided by the epsilon naught, which is the relativity of free space or vacuum. So the relative permittivity is equal to epsilon by epsilon divided by epsilon naught, right? So it is a ratio of permittivity of a medium and the permittivity of free space, right, or vacuum. So what is the value of epsilon naught? That is the permittivity of free space or vacuum. That is 8.85 into 10 to the power minus 12 Faraday per meter, or 1 by 4 pi epsilon naught is equal to 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9 into 10 to the power 9 Newton meter square per Coulomb square, right? So it is equal to 1 by 4 pi epsilon naught, that is the proportionality constant k in free space or in vacuum, which is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. Coulomb is the unit of charge, right? It's Coulomb square. So this is the value of proportionality constant in free space, 1 by 4 pi epsilon naught equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. So you can write the force, right, which is a vector quantity, or you can take the magnitude, right, which is 9 into 10 to the power 9 into q1 q2 by r square. This is the Coulomb's law for free space. So now we'll discuss what is electric field. So electric field at a point in a space is defined as the force experienced by a unit positive test charge placed at that point, right? So the force that is experienced by a unit positive charge in a field point is known as a electrical or electric field, right? So electric field is the force which is experienced by a unit positive charge, right? So it can be written as the force F equal to Q into E. E is the electric field, right? F is the force acting on the acting on the charge, right? The unit positive charge, which is a test charge, right? And Q is the magnitude of the test charge, right? So Q is the magnitude of the test charge, right, or the unit positive charge. F is the force acting on this unit positive charge, and E is the electric field. So F equal to Q into E. So the electric field E equal to F by Q, right? So the electric field can be expressed as the force experienced by a unit positive charge which is placed at a particular point, right? What is the unit of electric field? That is Newton per coulomb is the unit of electric field. Here electric field is F by Q, so unit of force is Newton and the unit of charge is Coulomb. So the unit of electric field is Newton per Coulomb. So it is basically a force which is experienced by a unit positive test charge placed at a position, right? So the electric field at a point in space is defined as force experienced by a unit positive test charge placed at that point. So hope it is clear now what is electric field. So now move to the next slide. Now we'll discuss electric lines of force. So what is electric line of force? So the path along which a unit positive charge would tend to move free to when free to so in a electric field, right? So it is basically a path along which the unit positive charge would tend to move when free to do so in an electric field. So if a point charge is free and it is allowed to move in an electric field, then it will follow a path. So this path along which a unit positive charge will move if it is free in a electric field. So this line or this path is known as a electrical line of force, right? So the line of force which is originated from the positive charge. So here you can see that it is originated from the positive charge and terminates at the negative charge. So if there is two charge, positive charge here and negative charge here, then it is originated from a positive charge and it terminates at negative charge, right? So the tangent to a line of force at any point gives the direction of force at that point, right? So if you draw a tangent to the line of force at any point which gives the direction of force at that point, right? So at that point the direction of the force is given by the tangent to the line of force, right? So the line of force is originated from the positive charge and it is terminated to the negative charge, right? So hope it is clear now what is electrical line of force. So now move to the next slide. So now we'll discuss what is electrical flux or electric flux. So the total number of lines of force originating from a charge which is equal to E dot A, where A is the area or E is the electric field, right? So this is a dot product E dot A. So this is EA cos theta, right? So the total number of lines of force which is called as a flux, right? Electrical flux or electric flux. Total number of line of force originating from a charge which is equal to E dot A. So dot product between the electric field and the area which is EA cos theta. So this is the total or the electric flux originating from a charge, right? So if you try to write it in integral form, the total flux phi equal to E dot dA. dA is the area, right? This is area, this is electrical or electric field, right? For the closed surface, the closed integral E dot dA, right? So electric flux is positive for diverging line of force, right? So for if it is diverging, the electric flux is diverging, then the flux is positive in nature, right? If the lines of force are diverging, then the electric flux is positive in nature. Whereas if the line of force are converging, then the electric flux is negative in nature. So hope it is clear now, right? So the total number of lines of force originating from a charge is known as a electrical flux, or which is represented as phi equal to E dot A, the dot product in between the electric field and the area. So it is equal to EA cos theta. right? And if the line of force are diverging, then electrical flux are positive in nature, and if the line of force is converging, then the electric flux is negative in nature. So hope it is clear now. So now move to the next slide. So now we will discuss what is electric potential, right? And electric gradient. So what is electric potential? The electric potential at any field point near the charged body is defined as the amount of work done in bringing a unit positive charge from infinity to that one. So the electrical potential is defined as the amount of work done in bringing a unit positive charge from infinity to a particular point near a charged body, right? Near a charged body, right? So what is the definition of electrical potential? That is the amount of work done in bringing a unit positive charge from infinity to a particular point near to the charged body, right? Hope it is clear now. So the electrical potential at a point near a charged body is defined as the amount of work done in bringing a unit positive charge from infinity to that point against the electric field, right? So V equal to W by Q or U by Q, right? Where U is the potential energy, which is in joule. So what is the unit of electric potential? That is joule per coulomb, right? Or it is called volt. So what is the unit of electric potential? The unit of electrical potential is volt, right? And what is the definition? That is the amount of work done in bringing a unit positive charge from infinity to a particular point against the electric field, right? So this is the definition of electric potential. Or what is the unit of electric potential? That is volt is the unit of electric potential. So now move to the next slide. So now we'll discuss electric flux density. What is electric flux density? That is amount of flux passing through unit area that is perpendicular to the direction of flux, right? So it is basically the amount of flux which is passing through the unit area perpendicular to the direction of flux, right? So D equal to phi by A. So this is the definition of electric flux density, right? So we will discuss electrical flux density. So electrical flux density is basically the amount of flux passing through a unit area that is perpendicular to the direction of flux. So D is called the electrical flux density, right? Which is equal to phi by A. So this is the relationship. Now we'll discuss the relationship between the electric field and the electric flux density E and D. So for free space, D equal to epsilon naught into E, right? Where D and E both are vector quantity. So D is electrical flux density, which is equal to epsilon 0 E. E is the electric field. So the definition of electrical flux density is amount of flux passing through a unit area A that is perpendicular to the direction of flux, right? For dielectric medium, D is equal to epsilon E, right? Or epsilon can be written as epsilon into epsilon R, right? So D is equal to epsilon into E, right? And the relative permittivity, which is equal to epsilon by epsilon naught, that is the permittivity of a medium divided by the permittivity of free space, right? So permittivity is basically gives the ability of a material to store charge or the ability to polarize, right? When it is exposed to a electric field, right? This is the relative permittivity. So for dielectric medium, the relative permittivity epsilon equal to epsilon r into epsilon 0, and the electric flux density D is equal to epsilon into epsilon naught into epsilon r into E, or D equal to epsilon E, which is equal to epsilon naught into epsilon R into E, right, for a dielectric medium, or you can write it D equal to epsilon E. So hope it is clear now. So what is electrical flux density? Electrical flux density is the amount of flux passing through a unit area that is perpendicular to the direction of flux, right? And this is the relationship D equal to epsilon naught E for free space, the relation between D and E. And for dielectric medium, D is equal to epsilon into E, or epsilon naught epsilon R into E, where epsilon R is the relative permittivity, which is equal to epsilon by epsilon naught. Hope it is clear now. Now moves to the next slide. So now we will solve some problem based on Coulomb's law, right? So we need to find out the force between two charges, 2 microcoulomb and 3 microcoulomb, which are placed at a distance 0.5 apart, right? So we will use Coulomb's law, which is equal to F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, and 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. And the charges are given. Q1 is 2 microcoulomb, which is equal to 2 into 10 to the power minus 6 coulomb, where Q2 is 3 microcoulomb, which is equal to 3 into 10 to the power minus 6 coulomb, and the distance between them is 0.5 meter, right? So F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, and 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. So put all the value in this equation, right? So F equal to 9 into 10 to the power 9, Q1 is 2 into 10 to the power minus 6, Q2 is 3 into 10 to the power minus 6, divided by the distance, that is 0.5 whole square, right? So Q1 Q2 by R square. So if you calculate it, you will get the force between these two charges, 2 microcoulomb and 3 microcoulomb, is equal to 0.216 Newton, right? So the force between two charges, 2 microcoulomb and 3 microcoulomb, which are placed 0.5 meter apart, is equal to 0.216 Newton, right? And as these two charge, 2 microcoulomb and 3 microcoulomb, both are positive, then the force is repulsive in nature, right? The positive charge and positive charge both are positive, so they repel each other. So the force between these two charge is repulsive in nature, and where the magnitude is 0.216 Newton, right? Did you get it? Now move to the next slide. So this is the problem number 2, right? Here two charges, 4 microcoulomb and 5 microcoulomb, repel each other with a force 0.9 Newton. Find the distance. So here there are two charges, 4 microcoulomb and 5 microcoulomb, which are separated by a distance. You need to find out this distance, and the force between them is repulsive in nature and have the magnitude 0.9 Newton, right? So what is the Coulomb's law? What is the mathematical form? That is F equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, which in free space or vacuum, right? So you need to calculate R, right? What is R? R is the distance between these two charges, right? So R equal to K into Q1 Q2 by F. K is 1 by 4 pi epsilon naught, which is equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. So R is root over K Q1 Q2 by F, right? Or K equal to 1 by 4 pi epsilon naught. So if you put all the value, so K equal to 9 into 10 to the power 9 Newton meter square per Coulomb square. What is the value of Q1? That is 4 microcoulomb, that is 4 into 10 to the power minus 6 coulomb. What is the value of Q2? That is 5 microcoulomb, that is 5 into 10 to the power minus 6 coulomb, and the force between them is 0.9 Newton, so 0.9. So if you calculate it, you will get the distance between these two charges 0.447 meter, right? So two charges, 4 microcoulomb and 5 microcoulomb, repel each other with a force 0.9 Newton. So the distance between them is 0.447 meter. So hope it is clear now. So now move to the next slide. So now we will discuss the Gauss law of electrostatics, right? So what is the statement of Gauss law of electrostatic? That is, Gauss law states that the total electric flux through a closed surface S enclosing a charge is equal to 1 by epsilon 0 times, that is equal to the 1 by epsilon naught, right? 1 by epsilon naught times the magnitude of the charge enclosed, right? So the Gauss's law states that the total flux through a closed surface area or surface enclosing a charge is equal to 1 by epsilon 0 times the magnitude of the charge that is enclosed, right? So phi equal to E dot ds, right? This is the total electric flux, right, through a closed surface, which is equal to 1 by epsilon 0 times the total charge enclosed by the surface, right? So E dot ds is equal to q by epsilon naught. So this is the statement of Gauss's law, and E dot ds equal to q by epsilon naught, that is the total electric flux is equal to q by epsilon naught or 1 by epsilon naught time into the total charge enclosed. So E dot ds, closed path integral, closed surface integral, E dot ds, that is the flux, is equal to q by epsilon naught. This is the mathematical form of Gauss law of electrostatic, right? So Gauss law become very useful in calculating electric fields in such cases where Coulomb's law or law of superposition becomes tedious, right? So it is difficult to calculate the electric field for such cases or such type of system by using Coulomb's law or law of superposition. In such cases, we can use Gauss law of electrostatic and we can easily find out or calculate the electric field, right? So this is the one prime application of Gauss law of electrostatic, right? What is the mathematical form? That is the closed surface integral, that is E dot ds is equal to q by epsilon naught. So what is the integral form? So E dot ds, so q, the charge, can be written as the volume integral v, the volume integral v, rho dv is the charge density into dv. The charge can be represented by this q equal to rho v into dv, right? So this is the volume integration rho dv. So we can write down E dot ds is equal to rho dv divided by epsilon naught, right? This is the volume integration, this is surface integration, right? Now move to the next slide. So let us consider a closed surface S around the charge q enclosed by a volume v, right? Then the charge density inside the volume is rho v, right? So here we now consider a closed surface S around a charge q enclosed by a volume v, then the charge density inside the volume is rho v, right? So rho v, so we can express q in terms of the charge density rho v, right? So q is equal to the volume integral rho into dv, right? So we can write E dot ds, the surface integration of E dot ds is equal to the volume integration rho dv divided by epsilon naught. The epsilon naught is the permittivity of free space, right? So now we can use the Gauss's divergence theorem, which is basically converts the surface integration to the volume integration, or surface integral to the volume integral, right? So E dot ds is equal to divergence E into dv, right? So by using Gauss divergence theorem, we can write E dot ds is equal to divergence E into dv, right? The surface integration is converted into the volume integration, right? E dot ds is equal to divergence E dv. So the surface integral E dot ds is equal to the volume integral or volume integration divergence E dv. So now we will replace this part to the volume integration, that is divergence E dv. So move to the next slide. So the divergence E dv, the volume integration divergence E dv is equal to volume integration rho dv divided by epsilon naught, where rho v dv divided by epsilon naught, where rho v is the volume density of charge, right? So for an arbitrary volume dv, we can write down divergence E equal to rho v epsilon naught or rho epsilon naught, right? Where rho suffix v, this is rho suffix v is the volume density of charge, right? So we can say divergence E is equal to rho by epsilon naught or rho v by epsilon naught, where rho v is the volume density of charge, rho suffix v is the volume density of charge, right? So divergence E equal to rho suffix v divided by epsilon naught. This is the differential form of Gauss's law of electrostatics, right? Or divergence D equal to rho suffix v. So you know that for vacuum D is equal to epsilon naught into E, right? We have discussed this formula. D is equal to, which both are vectors, D is equal to epsilon naught E, right? So electric flux density is equal to epsilon naught, that is the permittivity in free space, into the electric field. So we can replace epsilon naught E by D, electric flux density, right? So divergence D equal to rho suffix v. So these 3 or 4 equations are known as a differential form of Gauss's law of electrostatics, right? Now move to the next slide. So in this lecture we have discussed about the electric charge and its property, the electric field, electric lines of force, and electric flux. Electric flux phi equal to E in surface integration E dot dA. dA is the small elementary area and E is the electric field, right? We have discussed electric potential and electric flux density. We have also discussed electrical or electric field. We have discussed Gauss law of electrostatics, right? We have also discussed the Coulomb's law, that is the force between two stationary point charges, right? F equal to 1 by 4 pi epsilon naught q1 q2 by r square, right? We have also discussed the differential and integral form of Gauss law, right? So what is Gauss law? That is E dot ds, the surface integration E dot ds is equal to q by epsilon naught, right? So q is the charge enclosed by the surface and epsilon naught is the permittivity of free space, right? So we have discussed all these things in this lecture. So thank you for your patience.